In the previous lessons, we saw that the Caesar cipher, elegant as it is, falls apart under even a casual attack. Its keyspace is tiny, and worse, the structure of the language survives the encryption almost untouched. The Vigenère cipher is the historical answer to both of those weaknesses. For roughly 3 centuries, it was considered completely unbreakable, earning it the rather grand French nickname Le chiffre indéchiffrable, the indecipherable cipher. A little history first, before we dive into how it actually works. The cipher was first described back in 1553 by an Italian cryptographer named Giovanni Battista Balasso. Decades later, however, it was wrongly attributed to the French diplomat Blaise de Vigenère, and the French name stuck, even though Vigenère himself had actually invented a slightly stronger variant of his own. And it quickly earned its grand French nickname, Le chiffre indéchiffrable, the indecipherable cipher. And the name stuck because the cipher genuinely lived up to it. For roughly 3 centuries it stood unbroken, until Charles Babbage and Vigenère Cipher independently worked out how to crack it in the 1800s, but that story is for a later lesson. So what exactly makes Vigenère different from the Caesar cipher we already know? Caesar is what cryptographers call a monoalphabetic substitution cipher. There is one fixed shift, and every single letter of the message is encrypted using that same one shift. Vigenère, by contrast, is polyalphabetic. The shift changes from one letter to the next, which means the very same plaintext letter can become several different ciphertext letters depending on where it happens to appear in the message. And the pattern of those shifts is driven by a secret keyword. We write the keyword underneath the plaintext, repeating it over and over as many times as needed to cover the whole message. And here is the key insight. Each letter of the keyword effectively selects a different Caesar alphabet to encrypt the plaintext letter sitting above it. Vigenère, in a very real sense, is just 26 Caesar ciphers braided together. To actually use Vigenère by hand, historical cryptographers leaned on a lookup table called the tabula recta, Latin for upright table. Across the top we lay out the plain alphabet in green, and down the left side the key alphabet in purple. And the body of the table is filled with every Caesar shift of the alphabet, stacked one row beneath the next. The first row is shifted by 0, the next by 1, the next by 2, and so on all the way down to 25. Every single row is itself a complete Caesar alphabet. To see how that turns into encryption, let us encrypt the letter R using the key letter P. We pick out column R across the top and row P down the side. And where they meet, we find the letter G. So R, encrypted with key letter P, becomes G. That is the entire encryption, one lookup, one ciphertext letter. Let us try one more, just to be sure. To encrypt E with key letter A, we pick column E and row A. And the cell holds the letter E itself, because a key letter of A means a shift of 0, and a plain letter passes straight through unchanged. Let us put the whole thing together with a worked example, and we may as well pick a French word to fit our French cipher. We're going to encrypt rendezvous using the keyword Paris. First, we write the keyword Paris underneath the plaintext. The plaintext is 10 letters long, but our keyword is only 5, so we simply repeat it, Paris, Paris, until every plaintext letter has a key letter sitting beneath it. The length of the keyword, in our case, 5, is called the period of the cipher. Now we encrypt the message one letter at a time. For each plaintext letter, we look up a row of its key letter in the tabula recta and read off the cipher letter underneath. Let us walk through them all. R shifted by P gives G. E shifted by A is unchanged, still E. N shifted by R gives E. D shifted by I gives L. E shifted by S gives W. Z shifted by P gives O. And notice that Z has wrapped around the end of the alphabet. V shifted by A is unchanged, still V. O shifted by R gives F. U shifted by I gives C. And finally, S shifted by S gives K. And there is our ciphertext, GEELWOVFCK. Now look closely at the 2 E's in the original word rendezvous. The first E became another E, but the second E became W, because the two of them happen to fall under different key letters. The same plain text letter has produced two completely different ciphertext letters, and that, in one tiny example, is exactly what defeats the frequency analysis attack that broke Caesar. So let us step back and recap exactly what Vigenère has given us over the humble Caesar cipher. The first big improvement is keyspace. Caesar offers only 25 possible keys. You could even try every single one of them by hand in an afternoon. Vigenère, with a keyword of length m, offers 26 raised to the power of m possible keys. Even a tiny keyword of just 5 letters already gives us nearly 12 million possible keys, far more than enough to make brute force search by hand completely impractical. But the second improvement matters even more, because each plaintext letter is now shifted by a different amount. The frequency distribution of the ciphertext is smeared out. The telltale spikes that betrayed Caesar, E in particular, are simply gone. The classic single alphabet frequency attack just does not work against a polyalphabetic cipher, and for roughly 3 centuries, that was more than enough to make Vigenère look completely unbreakable. In the next lesson, we pick Vigenère back up and see how, after 3 centuries of looking unbreakable, Babbage and Kasiski finally managed to crack the indecipherable. If you want the rest of this cryptography course, hit subscribe so YouTube tells you when the next lesson drops, and a like on the way out helps other learners find it.